Awesome, awesome. Okay, thanks again. This is like today's small group, but I think very strong group as well. So hoping to have some fun discussions. We have Kartik, Nayak. I'm actually curious before we start, Kartik. I know that you're at Duke. I think one of the top researchers in the field. So I know a lot of people want to do their PhDs with you. But I think you're also at Espresso. I'm curious what the division of your time is there and how you spend your time, basically.
So I've been working with Espresso. I've been advising them for a long time. Right now, I think I'm doing a sabbatical. So half of my time is at Duke and half of my time at Espresso. But generally, I guess even before this, I've been advising them for a while.
That makes sense. Okay, I did not know that you were on sabbatical, which is awesome. I guess that's why we're seeing a lot of you all over the place, giving a lot of podcasts and talks. So please keep it coming. We want to absorb as much knowledge as we can. This is also the point for this. So okay, so today you're presenting this pipes model that I think is more or less recent. So okay, let me give the quick TLDR of. So I've spent some time reading it. So what I liked a lot about this is my view of kind of distributed systems in general has and how they scale has always been through the universal scalability law, which is kind of the reverse. So I feel like your pipes model is a predictive model. Whereas the other one is more of a statistical model. So it's like, okay, here we have these curves of, like kind of load or as the number of nodes and increases versus the throughput. And then we just model a curve on those. And then it's basically Amdahl's law, but adding another term for coherence. So the two main things that kind of limit the bottleneck, they argue is contention on a shared resource, and then coherence where you have to kind of send the data over to other people. And I was asking Claude a lot, and a lot of the formulas that come out of your paper, we kind of see this distinction between the distinction between the bottleneck terms with the contention, which are, let's say, the leader bottleneck is kind of one of those places, and then the coherence is more, oh, we need to send these blocks, propagate these blocks. So I like this a lot because it's like, okay, before all we had is fitting curves to predict this, but here what we have with your model is we have something that we can do theoretically at the outset. So even we could potentially have once we have a quint or a TLA spec of protocols, we can directly kind of, just predict where the bottlenecks will be. So I'm curious if this fits the way you're thinking about this. And
So to be honest about it, I guess, first of all, I'm very happy to be here and talking about pipes. But I think, I guess, first off, to answer your question, I guess I haven't thought of it in, I think in the way you described at all. And I think I'm not aware of any of those models. So I guess all of our analysis is actually, first principles based, where we just said, okay, how should things progress, and then let's try to come up with the model. So, and this goes back a little bit to, I think in the last 4 or 5 years, there has been a lot of talk about, I think my protocol performs better versus your protocol. And there are a lot of discussions that happen, where I guess the evidence that is presented is kind of anecdotal to say, I think I took my protocol, I deployed it in this particular experiment, and it performed well. So at some level, that helps, but at the same time, it does not tell me, I think what aspect of that protocol actually did well versus not. And over here, all through, I mean, I'm going to get into into this in my talk as well. I guess there has been a good amount of discussion on leader-based and DAG-based protocols, and at some level, all through my years, I've been on camps where, okay, this should do well versus that should do well. But, is there a fundamental way of thinking about it on what does well under what conditions? So I guess that was kind of the motivation for me to start thinking of this problem. And I guess around a couple of years ago when I met Andy, and I mentioned this to him, and he had similar reasonings as well. And I guess we kind of clicked and we said, okay, we should work on this together and figure this out from a first principles basis. By the way, I think Andy has given a talk on this topic as well, I believe at the SBC workshop last year. So if you heard a talk from him, there's actually a complementary talk to what he has presented. I guess the core content of what I'm going to present is not the same as what he did, and vice versa.
Interesting. Okay,
So
that's all.
I guess the goal for me is that, this model is a tool. Okay, I'm not here to optimize protocols. I'm not here to say, this protocol is uh, can be done better versus not, which is what a typical talk by me would be in this space. Over here, it's just a dumb tool. Okay, not dumb, but it's just a tool, but that you can, apply to any protocol that you're interested in. And today I'm going to present, tutorial for how to use this tool by using an example. Okay, so
That-
let me start from the beginning.
I'm sorry, I just want to say I apologize. I committed the biggest blasphemy of injecting my thoughts and my opinions into this. I will shut up from now on and bring back my question at the end, but I think that perfectly answered my question. So thanks for the introduction.
Sounds great. So the problem that we are talking about, I guess most protocols that we analyze over here, they fall in this general regime of state machine replication, where a group of parties agree on a sequence of transactions submitted by external clients, and they do so even if some of these parties are faulty. So in this model, you imagine there are transactions that keep coming into the system, and these parties run some consensus protocol among themselves to agree on the next block that is agreed upon, and you keep doing this over and over again to form your quote unquote blockchain. There are two key properties that you're looking at. One is called safety, and the other is called liveness. Safety says that nothing bad happens. Two non-faulty parties do not learn a different sequence of transactions. And liveness says a transaction that is proposed by a client will eventually be executed by every non-faulty party. And typically with an SMR protocol, you want safety and liveness even if some of these parties are Byzantine. Typically you assume T out of N are Byzantine, and you talk about this under different network conditions, synchrony, partial synchrony, asynchrony. Okay, so in this talk, I'm going to talk about not what Byzantine parties can do and what is the best way we can deal with it. What we're going to talk about is performance of these protocols. Okay, and in terms of performance, traditionally there have been two metrics that have been considered. One is the round complexity of the protocol, so called latency. So typically, traditionally this is measured in rounds. And typically you say, if a protocol requires 10 rounds of communication, then it incurs a latency of 10 delta time. Again, I think I'm shrugging, if you're talking about there being clock synchronization, etc., it may not be 10 delta, it may be a little higher and so on. But ignoring that, roughly speaking, the latency over here is 10 delta time. And in particular, how much data is transmitted is typically not considered when you're computing these latency metrics. They're completely ignored in these latency calculations. Okay, so even if you look at your synchrony assumption, or whenever or under partial synchrony, whenever messages are sent, we say a message that is sent by the sender arrives within some delta time. Okay, where delta is a fixed parameter. So think of delta as being 1 second, if you will. I think a natural question is this assumption even reasonable? And in particular, what if your message length is 1 terabyte long and you have a network that is 1 Gbps? Right? At that point, for a synchronous protocol, well, you may even lose safety in this process. And for a partial synchrony protocol, at the very least, I think you will not be as performant. But when you're thinking of the term round complexity or latency in this form, you kind of ignore the amount of data set. Okay, so do we ignore this information altogether? No, we have a companion metric called communication complexity, which actually deals with this question. So communication complexity is the number of bits that can be communicated by honest parties. Okay, so it takes into consideration the effect of sending large amounts of data by honest parties. And intuitively, right, I guess you want low latency, you also want low communication complexity. Intuitively, if you're sending lesser amount of data, it should take lesser time, and you should be able to send more realistic, more transaction level actual data, and you should obtain high throughput as well. So reducing communication complexity intuitively should reduce throughput, as well as should increase throughput as well as reduce latency. And that is, I think that is something that we at least when I have been working in the space, that is something that is what we have always been striving to do. Go ahead, Samuel.
Yeah, I have a quick question. I'm just curious about what about asynchronous protocols? How do they analyze any of this, or do they just not talk about latency at all? Because the big delta only applies to partial and synchronous, right?
So under asynchrony, you always say, I think messages arrive eventually. So when you talk about round complexity, you still say, it takes 3 rounds or 4 rounds or whatever.
I see. You still talk about rounds, just not, there's no kind of perfect.
And when you do experiments, I'll get to this. When you do experiments, you do show, okay, you have some throughput latency curves and so on. So experimentally, it's there. I guess you talk about latency, you talk about communication complexity, and all of it, does not change, I guess, across the network regimes. I see there are comments as well. Okay. Okay, so you have latency, you have communication complexity, and you want to reduce both of them, right? But still, you may end up in a situation in the following situation. Okay, so consider you have a protocol A. It requires 3 rounds of communication, and let's say it has n to the 4 communication complexity. And let's say you have a protocol B, which requires 5 rounds of communication, and it requires n to the 3 communication complexity. So we are saying both of them should be lower, but how do we weigh these metrics relative to each other? It's not at all clear. So it largely depends on which of these two, the rounds versus amount of data, which of these weigh in practice, and that can be a function of a large number of parameters and the setting that you're considering, what n is, what the delays are, and so on and so forth. Because of which the answer to this question may be different under different scenarios. Okay, and there's no easy way of talking about this today. So existing models for this reason, leave a gap, and this kind of came to the fore, at least in my head, when we were reasoning about these leader-based versus tag-based protocols in the past 3-4 years. So with leader-based protocols, you had this leader who was responsible for proposing blocks of transactions and getting all parties to agree on them. There is a line of work on leader-based protocols, for the past several decades. And if you look at these protocols, they actually achieve ideal latency or communication complexity. If you were to just talk about number of rounds, whatever is the minimum number of rounds that is necessary, in the presence of a good leader, you already get that with even just with PBFT. And even with communication complexity, you have hot stuff which just incurs a linear amount of communication. So if these are the metrics that these are the only metrics that we're talking about individually, you actually have protocols that actually do really well. But interestingly, it was observed that just having low communication complexity does not necessarily mean good throughput. And in particular, it was observed that leader may be a bottleneck under certain situations. And over here, I'm talking about vanilla leader-based protocols, where I think you don't do any sort of erasure coding techniques, etc. And this is what was measured in the Narwhal paper in 2021. So there were 2 key concerns, I think, when I look back now. I think I observe 2 key concerns with these vanilla leader-based protocols. One is, they perform unequal scheduling of work. So what does this mean? Let's imagine a leader is sending a 10 megabyte block to 100 parties. Then the leader is actually sending 1 gigabyte worth of information, whereas all of the receiving parties are only receiving 10 megabyte worth of information. Okay, so the leader is doing a lot more work. And if the leader fails, there is no progress in the view that happens altogether. And by the way, I guess this unequal scheduling of work, when I used to think of it, I always thought of the links in between these parties as being pipes. And for me, the way I would think of it is the leader's pipes are all full, whereas the receiver's pipes are empty. And that was the intuitive notion of how why I thought of these as pipes, and the eventual model is also called the pipes model. So over here, because of this, even if you have good communication complexity, we may not have good throughput. And DAG-based protocols, what they essentially did is they said, every party performs a similar amount of work at all points of time, and they, in a sense, they fundamentally solved this unequal scheduling problem. They basically said, everyone is doing the same amount of work, and they also said, okay, there is this DAG construction. I'm not going to get into the details of what DAG construction and what DAGs mean over here, but what does happen is that there is this progress that all parties do, because of which that progress itself does not depend on a leader, even if committing blocks does depend on the leader. Okay, and the disadvantage that they had was high communication complexity. But despite all of this, what they showed us is that, in practice, you have high throughput and low latency for moderate sized deployments. Did you have a question, Samuel?
Yeah, I had a question. So with respect to the unequal kind of scheduling and the leader being a bottleneck, I'm curious if you've looked at, like in Solana, there's this protocol called 00, which are basically kind of building an IP multicast layer. So you can think of basically you only need the data to go out once from the leader's pipe, and then the network itself has IP multicasting will kind of multicast it for you. So you can think of that as being like multicasting for free. I don't know if you ever thought or modeled those, because now you need to think if the network itself is being DFT, right, or something like that.
I think that's a good question. So again, I think pipes is a tool, and over here you can take any protocol and analyze it. So while we did not analyze that particular version of Alpenglow, I guess to me the closest counterpart over here is doing these erasure coded leader-based protocols. Even over there, I guess the leader does not have to do n times as much work in what I was presenting, and it kind of gives you a similar benefit. I mean, that particular protocol we did not analyze, but we could, I guess, with the techniques that we have over here. Victor, did you have a question?
Yeah, I guess it's a question for either you or Samuel. I guess I wasn't aware of like my since I'm kind of limited in my knowledge of the real world. Like I was, from what I've been told by people, is that except on a local area network, there is no hardware magic to get you this efficient multicast functionality. Are you saying something different, that nowadays Solana is able to get something like that in some configuration of their network?
Yeah, they have a dedicated sort of internet that is like separate. It's like not part of the public internet. They essentially rent out physical fibers and connect them to each other. And it's kind of like similar to how in high frequency trading, they have a separate network just for those messages. And so they build out their own network. And that's why they have this native multicast support as well. So I'm not quite sure. I think it's like very different from any sort of theoretical analysis where you have like n validators that talk to each other. Rather, it's sort of you have an explicit network in between them. And at each point in that network, there can be a multicast operation happening.
Right. So they're assuming some specific topology for their physical network. And
well, so 00 is not. It's not just a protocol. It's a physical deployment of fiber.
I see. Okay.
That's also why they call it another layer 0. But yeah, this is all off topic. So Kartik.
Yeah, it is off topic, but I think it's interesting to understand, like,
yeah, I agree,
how this impacts Kartik's model, for example. But anyway, that's out of topic.
Okay, so I mean, so to summarize, this is how we go about it today. So when I want to design an optimal protocol, I optimize for number of rounds and communication complexity. Okay, and by now I guess we have several protocols that give you O of 1 rounds for very small O of 1s, and poly and CC for a small poly n. Once you have this, you implement this protocol in practice. You have developers working on implementing this protocol, and then you deploy it on the cloud, in a geo-distributed manner, and run experiments on top of it. And at the end of this, you hope that you have good throughput and latency. Okay, so what we've seen is that just optimizing what you have on the left does not necessarily mean that you will always obtain good throughput and latency, and vice versa. And I guess this example of DAG-based protocols kind of tell you, even if you have high communication complexity, they can perform better for some parameterizations. So,
I guess,
go ahead, Victor.
Kartik, sorry, but I got, I remember when I was looking over a lot of literature in this area, you're right. I mean, there's kind of like this theoretical, two-pronged theoretical analysis, which you say people don't do enough to integrate, which is what you're doing here. And then there's some experimental analysis where people, I guess, kind of make up plausible stories about to explain the results of the experiment, and yeah, I guess when I was working on the simplex stuff, I did try to actually do some stuff which maybe could be seen as a primordial version of your pipes model, where just kind of doing explicit calculations, assuming a certain bandwidth and a certain latency and a certain way of sending out messages, and you get to kind of the same place. But of course, that was just like not a model; it was just a
yes, I completely agree with you.
Yeah.
But yeah, I think so. Coming back to what I was saying, you have this roundabout way of getting to you optimize something, you implement, run experiments, and then hope something else gets better. I guess the natural and these steps in between, I guess in terms of implementing and running experiments, they're typically expensive. I guess the natural question that we had was, can we directly optimize for what we are interested in? And that is where pipes model comes in. So over here, our goal is, or the question that we ask is, can we analytically, and I stress analytically, compute the trade-off between throughput and latency for a given protocol and a given number of processes? So in our model, we assume that there are n parties, and each of these parties are connected to each other in an all-to-all manner, where there is a delta delay between any two parties. Okay, every party has a bandwidth of s parcels per time slot, where S is both the upload bandwidth and the download bandwidth. And we assume that the system receives client transactions at the rate of d parcels per time slot. Okay, so given a fixed S, given a fixed D, given a fixed S, given a fixed N, given a fixed delta, I guess this allows us to link latency to D, okay, where D is the throughput. So if your protocol is actually running, is able to sustain this incoming client rate of d parcels per time slot, it implies that the protocol has a throughput of d transactions per second, or d parcels per time slot, right? So or said another way, if you fix d, you can find the relationship between latency and n as well. So this was the first time we were tackling this, so we made a lot of simplifying assumptions. So we're only considering the best case conditions where all parties are honest, where synchrony always holds, and in fact we assume that there's an exact delta delay between any two parties. Okay, that just does not change. We assume a zero computation time all through, but perhaps that is that could be easily fixed. And what we look at is the worst case latency for any transaction. So we have this worst case is over the stochastic arrival process of these transactions. So when a transaction arrives, it may make it to the next block, or it may just miss the current block and has to wait until it goes into the next block. So it is worst case in that sense. So the goal today is for me to maybe give one example in showing how to apply pipes analysis. Okay. So over here, the example I'm going to take is Braca's reliable broadcast. Samuel, you had this question on Twitter, why Braca's reliable broadcast? I wanted to pick the most boring protocol that one could pick, because, again, I think all we have is a tool. We can apply this tool to anything. And I wanted to pick one protocol that's not controversial in the sense of, if I pick one of the protocols from, I guess, one of the industrial blockchains, someone would say, hey, why not pick my protocol? So in that sense, this is just from a learning standpoint. So it could be anything, and it's Braca's reliable broadcast. Okay, so At a very high level, what does broadcast reliable broadcast do? It runs the protocol in 3 steps. The first step is where there is a designated sender or a designated broadcaster who proposes this block B containing some transactions. Every party receives this block, they echo this block and send it to everyone. In particular, over here, when you're echoing, you're sending the block contents as well. Then on receiving, some quorum of these echo messages, all parties vote on this on the block contents. And over here in this protocol, when you're voting, you just send a hash of the block on the network. And finally, on receiving sufficiently many votes, you deliver the block as well. Okay. If we do this, it gives you the nice properties of validity, totality, and agreement that is required for broadcast. We keep repeating this in our example. We keep repeating this over and over again with the same sender. Okay, so you run this at, you think of it as you're running this at depth t-1 followed by depth d followed by depth d+1 and so on and so forth. Okay, so what you see over here is a simplified specification. If you want to get into the details of exactly the exact protocol that we analyze, it is over here. So I'm not going to get into what this protocol is saying, but just one pointer is that if some flag over here, this flag is send equals true, is if flag send is true, that is when you check if the block size is equal to some parameter b, and if so, that is when you start broadcasting and working on the next block. Okay, and then after you deliver it, that is when you set the flag to be true again, so that you can process the next block at a later time. So as a first step, I need to set what this block size is. Okay, so a natural question is, how large should a block be? So think about the system where there is a sender. The sender sends a block to everyone, it gets delivered, right? And at the same time, there are transactions that keep coming in. Okay, so if you set the block size too small or too large, both of them are not great. Okay, so let's say it is too small. Okay, so let's say I set a 1 megabyte block size, and it gets delivered within 1 second. But if the incoming rate of transactions for me is 1.2 megabytes per second, at that point, at every instant, I'm going to have this 0.2 that gets accumulated, and over time, my latency will go to infinity. So if I set block size too small, then my transactions will accumulate over time. On the other hand, if I set my block size too big, let's say my block size is 1 gigabyte, and if its incoming rate is 1.2 megabytes per second, then whatever transaction has come in, it has to wait in the queue for a very long time before it is even proposed, and it will not have as good a latency. So what you want to set your block size as is, it should be large enough to process incoming transactions. Okay, so process incoming transactions so that there are no transactions accumulated, but you don't want to wait anything beyond that. So if you think about it, if let's say let's denote t star as the time to deliver some block at depth t. Okay, then it takes dt star time. Then within this time, you will receive, the system will receive dt star number of transactions in that time frame. So what you want to ensure is that the next time I'm proposing, I should clear my buffer so that I send all of these transactions. So your block size should be at least dt star. Okay, so this is the first constraint that we need. So what does t star look like? Okay, let's say the sender starts proposing the block at time t. Okay, I'm going to assume that my block has b transactions. and it also has some associated metadata M with it. Okay, so my block itself is B plus M in that sense. Okay, in this example, the sender sends it to all n parties. So it is sending B plus M times n amount of information, and it has an outgoing bandwidth of S. So it takes time, B plus N over S amount of time, just to clear it from itself. Okay, and after then, within delta time, within a delta delay, it will arrive at the destination. Right? All parties at this point are going to echo, and these echoes, you can perform the same analysis on these echo messages. Again, you're sending whatever you received in the proposal. So it's again a B plus M amount of information. And you're sending it to n different parties, and each of them we are assuming have a bandwidth of S. So it takes another, the same B plus N over S time to clear the buffer, another delta time. So the total is T plus twice B plus Mn divided by S plus 2 delta time. So note that there are n parties, each of who are doing this, but they're all doing it in parallel. So in that sense, the time does not add up across different parties. And finally, when everyone receives this, they all vote. And for voting, you incur this another n lambda. So the voting size over here, I'm assuming is lambda. So everyone votes, and it takes lambda times n divided by S time to clear the buffer, and another delta time for it to arrive. So everyone will deliver the block within this amount of time, and this tells us what a T star is. You started at T, and T plus whatever time it took, that's the value of T star. Okay, so once I receive this value T star, I can substitute it back in the inequality that I had earlier. And this gives me an expression on what B is. Okay, so what I'm doing over here is some simple rearrangement, where B is greater than or equal to D times blah divided by S minus 2nd. Okay, so I can set B to be anything larger than this particular value. So if I set B smaller, then more and more transactions will accumulate and latency will tend to infinity. So you want to set B to be at least so much, and ideally exactly this value, because otherwise your transactions are just waiting for them to be sent. Okay, so this is all about setting your block size. Once I have done this, I think you can start computing latency. So we compute the worst case latency for any transaction. Okay, and what does worst case mean over here? So there are transactions that keep coming in, and let us say, block of depth D minus 1 transactions for it are being proposed. Okay, and there is some point of time at which the proposer says, I'm done sending these transactions for depth D minus 1. And if a transaction arrives just after that, that is kind of the worst case time frame for a transaction to arrive. Okay, because now the transaction has to wait for depth D minus 1 to be processed, and then then it will be added to a block at depth D, and then block at depth D is delivered. So we need to compute the latency for whatever remains of. So you are in the process of processing D minus 1. So whatever remains in delivering D minus 1 and the time to deliver D. Okay, the analysis for this, how much time it remains, is very similar to what we did earlier again. Okay, so for depth D minus 1, you have already sent the block contents. Okay, you're still yet to send the metadata. So let's say T is the time at which the sender sends metadata for depth D minus 1 block. And this will arrive at all parties at time T plus Mn divided by S plus delta time. Okay, and then you go through this process of time for echoing and time for voting, and that gives you this time of T plus 2 Mn divided by S plus Bn over S plus N lambda over S plus 3 delta time. Okay, the calculations over here are very similar to what we did earlier. And then you go around and you process block of depth D as well. So this requires an additional time of 2Mn over S plus 2Bn over S plus N lambda over S plus 3 delta time. So the total time that is incurred is the total latency for this particular transaction. So this is latency as a function of B, but we know what the value of B is. So if we substitute the value of B, we will get latency as a function of D. Okay, I mean this looks like a lot, but it is just about simple algebraic manipulation. Okay, so now you have latency as a function of some constants, your metadata m, your vote size lambda, as well as some parameters, your bandwidth s, your network delay delta, and the incoming rate of transactions capital D. So if we just stare at this particular equation for a minute, right? So it is telling us something interesting. So first, if 2dn is small relative to s, okay, so at that point the denominator of the second term becomes very large. So the second part of the second term becomes 0. So the second term is 1. So latency is entirely determined by the first term, which is intuitively what you would expect. At low load, the amount of data that is sent is not playing a huge role. Okay, it plays some role, but not a lot, especially when 2dn is far smaller than s. But as 2dn approaches s, at that point, the denominator of the second part of the second term tends to infinity, tends to a large value. So the second term tends to infinity. And due to this, your latency tends to infinity. Okay, so we can plot this for whatever parameters of interest once we have it. Okay, so I can, so this is an example where we picked n equals 200, delta equals 200 milliseconds, a bandwidth of 10 Gbps, and some fixed transaction size and lambda. I don't remember. I believe m over here was 1,000 bits, if I remember it right. And given these parameters, you can plot a throughput latency curve without running any experiments. And the nice part is, I can just change this value to, from delta equals 200 milliseconds to delta equals to 10 milliseconds if I want to talk about, everything running in the same data center, for example. And I can visualize, how these protocols behave without running any experiments. So this is not to say that we should not run any experiments at all. I mean, eventually we should, because the model does make some simplifying assumptions. But this gives you, a much better explanation for how your protocol is behaving than what latency and communication complexity would do. So this is another graph where, so over here we fixed n, and we saw latency versus throughput. Over here we are fixing d. And as a function of n, we are computing latency versus throughput. All right. So in conclusion, you have number of rounds and communication complexity. They are indeed good metrics to determine performance of protocols, but they leave a gap. And with the pipes model, we are trying to analytically compute, the trade-off between throughput and latency, and we're trying to close that gap by looking at the protocol, in some more detail. So I guess the way I would think of it is, typically when we are designing protocols, it takes us a lot of time. You spend weeks or months trying to come up with the protocol and optimize it. And when we are trying to compute how the protocol performs, we end up spending 10 minutes looking at it. So over here with pipes, it's not going to be 10 minutes. It may be maybe a couple of hours or so, or more. But it's not going to be as bad as implementing and evaluating the protocol. You'll get a much better signal sooner for a little more work. Okay. So whatever I explained today, so we will put this put an explanation of this in a blog post as well on decentralized thoughts. And I'd be happy to take questions.
Okay, first question. If you go back to the previous slide where you had like kind of all, let's say, or even the previous one, I mean, whatever, one of those large algebra, yeah, this one's perfect. So even, you're calculating kind of the analytically, the expected block size or the optimal block size, let's say, given all of these things. But so in a real practical blockchain, the kind of, even the arrival rate is kind of changing. So all of these would be, like probability distributions. But is the trick that we can just kind of apply Little's law somehow and be like, oh, we're working with the mean of all these distributions, and B is the optimal mean? And then is this how you think about it, or you just not really think about it?
So I think, so over here we're assuming that transactions arrive at a fixed rate, and based off of this, I think you obtain everything in a clean way.
Right. Yeah, I'm just thinking like, yeah, if we try to extrapolate to a real network where or real queuing theory or something where kind of the input distribution is a distribution and it's not just always kind of constant, how would this extrapolate?
So I think I would say even if you change this to so the way we have written it, we say when it reaches B, that is when you propose a block. But I guess generally, if I were to say clear your buffer each time, that is such a protocol would work cleanly as well. I mean, at least for the scenario that we're considering, I guess everything should hold true if we just clear the buffer each time. Meaning, whatever transactions I have received, I'm going to propose them. I'm not going to wait. I'm not going to wait any longer, and I'm not going to leave any transactions up.
That makes sense. Victor, I think you had a question.
Yeah, question or more of a comment on your presentation. I mean, I've read through your paper, and one of the things I really liked about the paper, which I mean, you just kind of focused on Braca, which is good, but I thought it did a lot to give a really good quantitative analysis of the DAG versus leader-based controversy, and did so in a way that kind of boils down to a pretty simple qualitative story, which, if I recall, it's like for DAG-based protocols, the knee in your curve is further out, but before you reach the knee of the leader-based erasure-coded protocol, you're doing better than DAG, and that seems to be like a nice
yes,
kind of story.
I think in our paper, I guess we do the other side, and this is where I said I think my talk is kind of a compliment to what Andy did, because Andy covered all of those aspects already.
Yeah.
So I said, okay, I think this part, I think I want you to use the tool. So I think that's why I think I'm stressing on this aspect. Yeah, I think I do have a slide on this, I guess, on what Victor is describing. So going back to, I guess, this DAG versus leader-based thing. So the idea was, hey, the leader is slow because it has to send n times more data in a vanilla world. And whereas in a DAG-based protocol, everyone keeps sending data all the time, because of which you can obtain a good throughput, right? But the observation is that, I guess maybe this is, never mind. So, but the observation is that in a leader-based protocol, typically if you use erasure coding techniques, you can actually mitigate, not only mitigate, you can actually do significantly better, because now you're not sending n times more information, but you're only sending a constant times more information. Right? So if you're tolerating 1/3 faults, then typically you're only sending 3 times more information, or if you use some of Victor's recent papers, maybe 1.5 times more information compared to what you do need to send compared to your block size. Due to this, you're in an erasure coded protocol, your leader is no longer the bottleneck, due to which your latency and throughput can actually improve significantly. So, if you look at, so this is an example over here where Disperse Simplex is a leader-based protocol with erasure coding, and Sailfish is a DAG-based protocol. So in Sailfish, everyone proposes all the time. So the observation that Victor mentioned is, you have this latency that is very low compared to Sailfish, and but it shoots up faster. The reason why it shoots up faster in this particular protocol in what we analyzed is because the leader is sending 3 times more amount of information, because of which the maximum throughput that you can obtain, or the latency bottleneck, is a factor 3 smaller than what you could obtain when everyone is sending it. But within that regime, for the set of parameterizations that we considered, actually, if your throughput is small, it actually performs, better than Sailfish.
Yeah, and there was one other aspect that
Which-
I remember you explained to me once, which I thought was important, that I didn't see it right away, which was that in a DAG-based protocol like Sailfish, to get that high throughput, you need to have everybody broadcasting a block. But then the overheads, actually, it's much easier to be in a scenario where the overhead per block now is higher than it is when you have a single leader, right? I think that was one of the if you use the same, like if you have n parties and you're going to have the same transmission, the same throughput, so fix the throughput to be the same, then in simplex, say you're sending one huge block, and in DAG-based, in Sailfish, each party would be sending a block that's 1/n of the size.
Yes.
And plus metadata, which can in a DAG-based protocol,
Yes, yes.
sending out all these certificates and everything. So there was some calculation I did. I was either talking to you or one of your co-authors about it. It's like at some point those overheads in Sailfish can also start getting high if you in the limit, right? If you just fix the throughput to be fixed and let n go to infinity, then eventually yeah. So,
I mean, you have like these 2t+1 links that you have.
yeah.
But I think I think I agree with everything that you said. But I think I want to mention that I think although I have these curves, it's not an all apples to apples comparison over here, regardless, right? I mean, for a couple of reasons. One is, for a DAG-based protocol, when all of these parties are proposing in parallel, it may just so happen that two parties propose the same transaction, because of which your effective throughput is actually lower than what you have.
Yeah, that's another problem.
At the same time, I guess the other side of it is that in a leader-based protocol, if a leader has to propose all of these transactions do need to get to the leader in the first place. In this analysis, we are assuming that the leader already has these transactions. The system has somehow given it all of these transactions. So how do they get there needs to be considered.
Yeah. There's lots of other trade-offs too. Also in the blockchain space, one concern I know with DAG-based.
Exactly, and I think even over here, right? I think in this particular diagram that I have, so this is considered actually a very specific version of dispersed simplex. It's the most pipelined version of dispersed simplex, because for us, we wanted to see something that's offbeat. And I guess so Victor has this version of simplex where you fix a leader all the time and you pipeline the sending, as much as possible. So we are considering that pipeline single leader version of dispersed simplex over here, but we are not doing that for Sailfish. So in that sense, it's still a little apples to oranges in terms of what you can get. Right, but regardless, if comparison is not your goal, if just to figure out, how your protocol would do under a given setting is the goal, I think pipes will go a long way.
Yeah, as Tobias says, I mean, DAG protocols just have a bit more built-in latency than leader-based protocols do, just in terms of number of rounds of communication. Yeah. But anyway, I think it's a great model to have one. Reduce to really kind of combine these two metrics in a meaningful way, even if it's a little bit too much of a maybe some aspects of it are a bit idealized, but that's fine. I mean,
it's a start.
It's a great start. Yeah.
So I guess I see that on the chat. There are some questions or comments by Tobias, Samuel, and Patrick, I guess, in whatever order.
I think we already discussed those. I mean, you brought up the same points about like the limitations of DAGs. Yeah.
Okay, sounds good.
Yeah, I'm just asking the dumb questions with respect to DAGs. I'm actually surprised. I didn't even know that they have more rounds. I always kind of just assume like all the protocols on top of Narwhal are just doing consensus kind of a bit further downstream, just waiting for the data to have propagated. But I thought in the end they do the same thing. So maybe if there's like a 2-sentence summary of what they're doing and why there's more rounds, I'd be curious to hear.
You just have to kind of, at a minimum, you have to kind of do 2 rounds of reliable broadcast before you can get something committed. And then there are some papers like Sailfish and others who like reduce it to 1 reliable broadcast plus some cheaper thing.
So I think, yeah, I'll say that it's not. It depends on exactly what you're trying to get at. But I guess again, I think optimization is not the question of pipes. So we can have a separate discussion on, hey, can I get the same latency as a leader-based protocol in DAG-based protocol? Perhaps that's possible. So historically, yes, I guess in terms of if you use number of rounds, it has been small.
Yeah, that makes sense. I think I was making the mistake of kind of only considering the rounds of the consensus protocol part, but just forgetting that you also have to broadcast kind of the data first as the narwhal part. And you guys are saying the latency is like all of those rounds when you look at them together, right?
Yeah, I guess. So, again, I think narwhal is one way of doing it. You could do it, I guess, the way I believe Mysticity is doing it, or they did it. I don't know if they've changed, but I guess they did it like what they were doing at least a year ago, where you just transmit as a part of your protocol itself. So over there, I guess there is no separate dissemination. But again, I think, those are great points, right? I think when we are analyzing it, we should consider all of it and see the effect of what your protocol is going to look like.
So a question that's more relevant to your actual talk here now, we're getting off track, but I mean, it seems like a natural next step now is to take your pipes model. I mean, people have done experiments to compare different protocols, but now the experiments that should happen are like, how good of a predictor is the pipes model, and where does it need to be refined, perhaps, or complicated to take into account more real-world quirks that maybe haven't been taken into account here?
So 2 things, I guess. First part, I guess we already have in our paper. I did not stress upon it in my talk, but in our paper we do have an analysis that an experimental analysis that says, how our model matches up with what happens in practice.
Oh, okay, was that always there? Maybe I missed it the first
time.
No,
I think we put it up.
That was
sometime late last year.
Oh, okay. Maybe I didn't see the newer version.
So I mean, we did not do it for everything, but we did it for some protocols, and I guess so that is one. And I guess on the second part, it is something that we are thinking about it actively right now.
About what?
I guess on how to improve and where it can go off, and how to improve some of these simplifying assumptions. It is something that we are thinking about actively right now.
So what is this pipes pocket calculator, Patrick?
For the Minimit paper, we used a very similar model for doing the performance testing instead of actually doing like a real deployment, because we could control the network topology with like link control, like drops, like variance of like link speed and everything. And so we built this tool called the estimator using our like simulated deterministic thing. And it's very similar to the pipes model, but you can like run it as like a little CLI tool with like a kind of like a DSL describing different protocol specs. So this is what we used during the Minimit paper to like save us some time. Yeah.
Is this more of a simulation than an analytic thingy? Like,
so we have a tool to also do deployments to measure stuff and like compare it to the performance of this. But this is like really nice just to do like back of the envelope calculations on how like a protocol might work when it's distributed on like a certain topology. So like it's a good stepping stone to like doing like a full verification or something like that.
It's a symbolic, it's a calculator. It's not like running a simulation behind the scenes. It's just...
So it does do a full run of like a single round of like a protocol spec behind the scenes using like a fully virtualized simulated network that's built on top of all of the Commodore stuff. So yeah, we use it actually quite a bit for like back of the envelope calculations. It does it quite a bit. It's only one round though. So it doesn't do like a multi-round sort of step, but at least one round it will do pretty well. And like actually has virtual nodes that process things with virtual clocks and everything like that. Yeah.
So you would get estimates for specific configurations rather than a formula for
Exactly. Yeah. So the problem is like when you start to get into like modeling some of like the statistical performance and topologies, like it's tough to have a closed form solution, which would be great. I think you guys have made good progress towards that. This is like the engineer's approach, which is like no
Well,
formulas.
Yeah,
Just like let's actually model
plot a
the
graph,
network.
right? You
Yeah,
could
and
also
then
just plot a
average it.
graph and say, well, what if we increase the nodes from 100 to 200? What'll happen?
Exactly. So you can do all of those things.
Yeah.
So we have a few out of the box examples. Like we have Simplex, Kudzu actually, Minimint, and then also like Hot Stuff, I think, with like, so you can kind of see the difference in performance when you have like the leader bottleneck, or you do like an all-to-all broadcast, but maybe the all-to-all broadcast is bigger. So then it like gets caught up because the bandwidth is limited. So yeah, there's a lot of fun you can have with it if you want to like do a little bit more than just look at the paper, I guess. And so we've been using it on our side. I wouldn't say it's like a, you know, some magical thing, but it's fun to kind of play around with different protocol specs. Yeah.
I actually played around with it,
Sounds nice.
and I can sort of recommend it. It actually only takes like a few lines to, like if you have a protocol that has 3 rounds of communication, I think it only takes like 3 or 4 lines of code to write down that protocol and to simulate it. And yeah, so I actually played around with this a little bit, and because I got really interested in Minimit after you talked, Patrick. So these are, you know, again, as Patrick says, these are just kind of back of the envelope calculations. But what I found out is that the block time in Minimit is actually like more than 2 times faster than in sort of PBFT, Tendermint, you know, where you have 3 rounds, because you have this, you can move to the next view of just 40% of the votes, which and 1 round of voting, which is very fast. But then I kind of, and this is something I wanted to talk about, because I think it's something that we might have overlooked as a community. I realized that in practice, what matters is not so much the average, like for block time, it doesn't matter so much what the average block time is, right? So if you look at the, you know, like let's say look at the Alpenglow paper, they say they have a block time, they have, finalization of 150 milliseconds, but then the actual practical implementation on Solana is going to use a block time of 400 milliseconds. So they purposefully choose a longer block time. And you can actually kind of see why, because you want to have a paced block time, right? Like you don't want the block time to fluctuate between like 50 milliseconds and 400 milliseconds. You want to have the same block time in every view. And for that reason, what matters most is actually not the average block time that your protocol could achieve if it runs as fast as possible. What matters is kind of the worst case block time, right? So kind of what is the worst case, and then that's going to determine your block time. And if you do that, then the advantage that Minimit has over PBFT is only 20% actually. And you know, I love Minimit. I think it's a great paper. But I kind of was a bit disheartened when I realized that actually for practical deployments, we have this issue that the block time is determined by the worst case. And the worst case is the proposer is somewhere in Australia, and it's kind of dominated by the latency you get from just purely the speed of light of going to Australia. So I don't know.
I think it comes down to philosophy. We have people deploying things with variable block time.
Yeah.
So like
okay.
there's no goal to have like a standard block time. Because you have to remember, even if you do fixed, you can have skips. So like it doesn't mean that it's not going to be a steady block time. And oftentimes we see people strongly prefer responsive views rather than like a fixed view thing. So they have other reasons in Alpenglow why they prefer like a fixed time.
I don't know, but my understanding is that most blockchains choose to have a fixed block time. Of course, there's a timeout. You know, the timeout is longer, but like
I think it comes down to, at least what we've seen is a lot of people have thought more about fixed lately because it can help. I mean, you want to bound like the MEV on like the chain in some way. And so like by forcing a fixed time. So we in our models have like this, you can just basically tune the responsive timeout to like aggressively bound how long a responsive view can take. Some people believe that in practice, responsive protocols basically will drift to whatever the timeout is, because that will be the preferred like game theoretic outcome for like a leader to wait as long as possible to get their block out. Other people say, well, if blocks can go faster, people should prefer voting as soon as possible because that means more blocks, which means more fees, which means like more efficient markets. And so we've seen debates on both sides whether or not the default behavior will end up being trying to push the timeout or actually the opposite of trying to like go as fast as possible. Yeah.
Yeah, I think I saw a paper recently actually by Kushal from Category. So I think the incentive for the validators is to vote as quickly as possible, but the incentive for the leader is to propose as late as possible, because the longer you wait, the more transactions you can include, the more MEV you get. All these.
But I think the idea is that the claim is basically that by going even faster on the block latency, though, you actually reduce the time from basically for transactions to be finalized. Like, so basically the transaction confirmation latency goes down if you have faster views. And so it can be better to go faster because like the amount of the latency from a transaction creation to its finalization can be shorter if you have faster views, which for some people is actually better in terms of fee collection than like trying to batch and do longer. So yeah, I think it's more than just the voters dynamic. It's actually like the leader, the question, like, because for example, you brought up 00 before. The whole premise of 00 is that we can go faster. And as a result, fees will be better, the chain will be better. Like the same kind of premise applies to how you should think about what the default like economic strategy is for responsive performance. But yeah, I think like papers on this are, I think still very much like this is like kind of the frontier of like probably where MEV is right now, because a lot of teams have shifted to responsive or want to shift to responsive views. So we'll see. I think we'll see what those papers show. Yeah, but I would say I'm not as big of a fixed view person, but I think like there's more diversity in like view iteration preference, I think.
Okay, Kartik has the drop. That's really unfortunate. I had a question on the throughput. Maybe we can like continue on Twitter or something. I'll say thank you. Thanks a lot, Kartik. This was super insightful.
And thanks, guys.
Okay, I guess we can continue on Telegram. Victor, also please join the group so we can keep arguing on there.
It's a Telegram group?
Yeah.
Oh, is there an invite or something, or how do I?
Let me send you. I'll follow up on the email chain we have. I'll send you the.
Yeah, I've been forced to join Telegram, but I've been forced to like upgrade to a pro subscription so I can stop having, Russian girls sending me messages all the time to meet up. It seems like that's the only way you can avoid getting spammed by this stuff is to get a pro account so that you can dial down the spam. I don't know.
I think that speaks to yourself because I haven't had this problem. I think you're a superstar, so that's the issue.
Also, you guys, so it's Telegram, not X, because right now I can't even do X. I've been banned from X for ridiculous reasons. They have this weird policy now on X to like, if you, I think I made a mistake one time and I didn't have my. They thought I was a fake account, and for no particular reason. I mean, I wasn't trying to be a fake account, but some bot determined I was a fake account, and then they banned me, and I tried to create a new account, and then they figured out that I was the same person somehow, and they banned me again. So now I seem to be, even if I log in with a different email address or something, I don't know how they're tracking me, but they're somehow figuring out that it's me no matter when I join. So anyway, Telegram. Yeah.
It is Telegram. It would be nice. I'll make a phone call to Elon. Let's see if we can figure this one out.
Yeah, yeah, do that. Let me know. Yeah, let me know how that goes.
Sounds good. Thanks a lot, guys.
All right, thanks. Bye.
Thanks, everyone. Bye-bye.